We're going to do a lot of different homomorphisms today. It's in some sense the most important concept in group theory. So a homomorphism is something that goes from one group to another. And it's a map of sets which has the property that it takes one multiplication into the other. So f of g times h is f of g times f of h, where this multiplication takes place in G, and this multiplication takes place in G prime. So analogy is like a linear map between vector spaces. It takes the addition in one vector space to another. It takes scalar multiplication to another. Now, some simple properties of homomorphisms which you establish in the homework is that it always takes the identity to the identity. And if you apply it to the inverse map, G inverse, that happens to be the inverse of f of g. So once you have this property, this is the only thing you need assume. I mean, you'd want all of these properties if you preserve the group structure. But once you assume the property that it takes one multiplication into the other, it immediately follows that it takes the identity into the identity, and it takes inverses into inverses. To prove that it takes the identity into the identity, you use the fact that in a group, E times E is E. E is the only element which has that property. No other element has the property that A times A is A. Okay, this is a unique element with that property because you could cancel E by multiplying by E inverse. So if you take that and you apply F to it, you get F of E times F of E using this property. That's F of EE. So maybe I should have written that down. F of EE, which is F of E times F of E, is equal to F of E. Applying F to both sides of this identity, and then using the homomorphism property. And then we see that F of E has that property in the group G prime. So multiplying by F of E inverse, you see that F of E is E prime. Okay, you guys did all this for homework. Same thing, I'll let you do the inverse one yourself. It's from the unique property of inverses. Now, some important things about homomorphisms is that if we could have another homomorphism to G double prime, and the composition H of F of two homomorphisms is a third. And we're going to see that a lot today, that when we compose two, because if you have this property for F and you have this property for H, you'll see that you have this property for the composition of two. And some important subgroups that are associated to a homomorphism, you have the image. Peter defined last time, so that's the set of elements of G prime, which are equal to F of G in G prime. So they're the things that are hit by the homomorphism. And that's a subset of G prime. And you have what's called the kernel. And for those of you who've done vector spaces, you know this sort of thing. That's the set of G such that F of G is the identity element in G prime. And that's a subgroup, that's a subset of G. Just like you have the kernel and image of a homomorphism of vector spaces. And if both of these are the trivial element, if the image is, so if image is equal to G prime and the kernel is equal to the set E, which is always in the kernel, the image always contains E prime by the fact that F of E is E prime, and the kernel always contains E. So if the image is G prime and the kernel is E, we say F is an isomorphism. And beyond being an isomorphism, if G is equal to G prime and F is an isomorphism, we say F is an automorphism, an isomorphism from G to itself. We'll give some examples of that. Now, I think in homework you showed that these are both subgroups of a group. Is that right? Both subgroups. And on the other hand, the kernel is a special kind of subgroup, which we'll usually use this symbol to denote not just subset, but subgroup. But the kernel is a special type of subgroup, which is called a normal subgroup. A normal subgroup, H in a group, and it's denoted this way, not just by the contain sign, but a little triangle. So it means it's better than just a subgroup. It has a nice property. Has the property that if you take any G and G, for all G and G, if you take the conjugates of H, well, GH, G inverse, let's do it that way. That's another subgroup of G. You can easily see that that's closed under multiplication, because if you multiply GH, G inverse by GH prime, G inverse, then these two G's cancel, and you get G times HH prime, G inverse. So this set, all elements of the form G, an element in H times G inverse, is closed under multiplication. So it's another subgroup of G. A normal subgroup is one where this is always equal to H. So we might say, if we call this multiplication on the right by G and on the left by G inverse conjugation, because that's what it is, then we might say the normal subgroups are closed under conjugation. By all elements G and G. It's clear it's closed under conjugation by elements in H. If you multiply an element in the H, an element in the subgroup H on the left by H and on the right by H inverse, that's still in H. But this is amazing that it's closed under conjugation by G. And that's true of a kernel, but not of an arbitrary subgroup. That's a really important distinction. It was first noted by Galois, who I told you developed group theory. So let's check that the kernel is a normal subgroup. It's easy. So if we have an element G in it, well, let's say H is in the kernel. We have to check that GH, G inverse is also in the kernel. So we apply F to it. F of GH, G inverse, using the homomorphism property, is F of G, F of H, F of G inverse. Now the fact that H is in the kernel means that F of H is the identity element. So this becomes F of G times the identity element times, and F of G inverse is the inverse of F of G, which is just the identity element. So that's why the kernel is closed under. Now if you want to see an example of a subgroup that's not normal subgroup, take the following subgroup. So this is just an observation. When you make a mathematical definition, you should always see whether it actually narrows the field or not. Maybe all subgroups are normal. Maybe this property is held by everything. So you have to actually, to see that this is a distinguished character of subgroups, you have to exhibit a non-normal subgroup. Now you can't do that in an abelian group. In an abelian group, this is obvious because G commutes with H. So you can move the G over to this side and cancel the G inverse. So you have to go to a non-abelian group to get a counterexample to a normal subgroup. Can someone suggest a simple non-abelian group to work with?
Like S3?
S3. So let's take a look at S3. And let's take a simple subgroup to work with. Let's take the identity element and our transposition tau, where tau sends 1 to 2, 2 to 1, and fixes 3. Okay? Now, I claim this is not normal. So you have to find an element in the group that takes this subgroup outside of itself. Well, let's try something. Let's try conjugation by tau prime, where tau prime is the element that switches 2 and 3 and fixes 1. So tau prime clearly takes e to itself when you conjugate. But what is tau prime, tau prime inverse? Well, tau prime inverse is the same as tau prime. So we're calculating tau prime, tau prime. Well, let's see. If it's this element, we'll be able to tell by just evaluating it on 3. Because this is the unique element in the group other than the identity that fixes 3. So let's see if it's tau or not. So we'll apply it to the element 3. Tau prime of 3 is 2. So this is tau prime of tau of 2. Tau of 2 is 1. So this is tau prime of 1. And tau prime of 1 is equal to 1. So this element does not fix 3. It takes 3 to 1. So in particular, it's not equal to the element tau. In particular, in fact, it's the other transposition. It's in fact equal to tau double prime. One can figure that out pretty easily. It has to, we'll see later. Well, I mean, this has to be conjugated into a subgroup, and there are only 3 subgroups of order 2 in this group, generated by E and tau, generated by E and tau prime, and generated by E and tau double prime. And tau double prime is the unique one of these things that takes 3 to 1. Okay? So in fact, we find here that tau H, tau inverse, is the subgroup E tau double prime. And so there's a non-normal subgroup for you. So in particular, that subgroup is not the kernel of a homomorphism. That subgroup is not the kernel of a homomorphism. Okay? So now let me give you some examples of kernels and images. Yeah?
Is that an if and only if? Like, if a...
Go say it.
So if you have a normal subgroup, is it necessarily the kernel of the homomorphism?
Yes, but that's a theorem. We have to prove that. Right now, all we know is if we have a homomorphism, its kernel is normal. One of the big observations we're going to get to is if we have any normal subgroup, there's a homomorphism which has it as a kernel. Okay? That's big. But we haven't gotten there yet. But good anticipation. Others. Let's see some homomorphisms and figure out what their kernels are, etc. By the way, homomorphisms are much more important in group theory than groups. It's a general phenomenon. When you study a little bit more math, you'll study things called categories. So categories have 2 things in them. They have objects and morphisms. So category of vector spaces, the objects are vector spaces. The morphisms between vector spaces are called linear maps. Category of groups, the objects are groups, and the morphisms between them are called morphisms. Category of topological spaces, the objects are topological spaces, and the morphisms are homomorphisms in the category of, category of differentiable manifolds. The objects are manifolds, and the morphisms are differentiable maps. So it's a sort of meta-mathematical concept. Now, when you study categories, the objects are irrelevant. Everything is about the morphisms. So you're going to see that in group theory too. Everything's about the homomorphisms. We're going to encapsulate everything about groups in homomorphisms. So here's one. So if you take the group G as GLNR, and we have a homomorphism F to the group G prime, which Peter called R star, which you could also call GL1 of R, invertible 1-by-1 matrices over R, which takes F of a matrix A is the determinant of A. And that's because the determinant of B is the determinant of A times the determinant of B. So the key rule is the determinant of AB is the determinant of A times the determinant of B. And this is multiplication in our original group GLNR, and this is multiplication in our group GL1R. Now, you should review why this is true. There's an elaborate description of this in Chapter 1, which I'm not going to go into. It's because the determinant is a unique map of a certain type. And then you check that when you apply it to the product of 2 matrices, the only way it could be unique is if it works out this way. That's the right way to prove it. Take a look at the material in Chapter 1 to review that. This map has image you can get down a matrix with any determinant. So you have to prove that. If I want to hit some real number, can someone give me a matrix which has that determinant? Yeah. You want to try?
You could take the identity with the first, the upper left.
Exactly. If I want to make an element with determinant lambda, I take this matrix, and the determinant of this matrix is the product of the diagonal entries, which is lambda. Okay? Good. So that's the proof of the image. The kernel of F is not all of GLNR because things have arbitrary determinant. It's the matrices which have determinant 1 because the identity of this group is 1. So it's A such that the determinant of A is equal to 1. And that's a subgroup because of this property. And it's a normal subgroup. If you conjugate a matrix with determinant 1 by an arbitrary matrix, you still have something of determinant 1. And this group is a very famous group in math. It's called SLNR. This is called the general linear group of dimension n. This is called the special linear group of dimension n. Okay?
Could you repeat that point about conjugating?
Yes. If you take a matrix A, such the determinant of A is equal to 1, and you calculate the determinant of the matrix B inverse, for any invertible matrix B, that's what I mean by conjugating by an element in the group. We're checking that it's a normal subgroup. Then this becomes the determinant of B times the determinant of A times the determinant of B inverse. Right? But the determinant of the quantity B inverse. But this is the same as the determinant of B inverse. And this multiplication takes place in a commutative group. So this is actually the same as the determinant of A, because the determinant of B commutes with the determinant of A. It's in a group where the multiplication law is commutative. So in this case, it's even stronger. Not only are the things of determinant 1 stable under conjugation, which would be true in any case, but the things of a fixed determinant are stable under conjugation. That shows that this subgroup is a normal subgroup. So I would denote it like this. Okay? Now let's do a little bit more serious homomorphism. This is an extremely important homomorphism in group theory. We have two general groups that we know about, GLN and SN. So we should have a homomorphism between them. So I claim there's another homomorphism from the symmetric group on n letters to the group GLNR, which takes a permutation sigma to a matrix A sigma, which is called the permutation matrix, and I have to define it for you, associated to sigma. And it's an unusual matrix. And it looks like this. All the entries of this permutation matrix are zeros and ones. And in the jth column of this matrix, notice this n is the same as this n. So in the jth column of this matrix, you have an entry which has got all zeros and it has 1, 1 in it. And the 1 occurs in the place that sigma takes j to. So this occurs in the sigma of jth place in this vector. So each column is all zeros and 1, 1. And the 1 tells you where the permutation takes j. I'm going to do an example so you see this, because in this notation it can be a little confusing. So let us take a permutation in the symmetric group on 3 letters and write down its permutation matrix. Example, G is equal to S3, and sigma is the thing that cycles the things around. 1 goes to 2, 2 goes to 3, 3 goes to 1. That's a good permutation. its permutation matrix, according to this definition, as follows. In the first column, you see where you take 1, it takes it to 2. So the first column looks like this. 1 occurs in the second place. In the second column, you see where it takes 2. It takes 2 to 3. So you put a 1 in the third place. And in the third column, you see it where it takes 3. It takes it to 1, so it looks like this. So not only does every column have just 1 in it and rest zeros, every row has just a 1 in it and the rest zeros, because it has to go to somewhere. And it's a permutation. So this would be the matrix A sigma. Now, one thing you have to check that this is a homomorphism. So that you have to check that F, when you apply F to the permutation sigma tau, you get A sigma times A tau, where this is composition of permutations. And this is matrix multiplication, because that's the multiplication law there. And that's a simple check about multiplying two matrices of this incredibly simple form. So I'll let you do that. The book checks it too. And if I got it right, they'll multiply correctly and not their transposes multiply correctly. Okay, so this is a critical homomorphism for us. And let's see what its image is. Clearly not everything in here. So the image is what called permutation matrices. It's the matrices that have exactly 1, 1 in each column and 1, 1 in each row. Because if I had such a matrix like this, right, I could associate to it a permutation. Right? It would be the one that took 1 to 2, and 2 to 3, and 3 to 1. And the setting up of 1, 1 in each row and column exactly says that that's an invertible map from the set of n elements to itself. So the image is the permutation matrices. And the kernel is just the identity matrix. That's the simplest kernel, because the only matrix that goes to the identity along the diagonal is the one which is the trivial permutation. It takes 1 to 1, 2 to 2, 3 to 3. Okay? So I'll ask you to check, and the proof is given in Artin in the first chapter, that this rule holds. That's the way I've set up permutation matrices. And this gives us a very interesting subgroup of the symmetric group, because I claim that the determinant of any permutation matrix is equal to plus or minus 1. The determinant of a permutation matrix is plus or minus 1. Well, if you know the horrible formula for a determinant where you sum up n factorial things, there's only one of those things that's going to be non-zero. It's going to be a 1, because it's going to be a product of the entries. And it's going to come with a plus or minus sign. So the determinant is plus or minus 1. And if we can show, by the way, the determinant can be minus 1, if you take a transposition which says takes 1 to 2 and fixes everything else, so that's our simplest elements in the symmetric group that move anything, then as a matrix it looks like this. And then it has 1s the rest of the way down the diagonal. So the only off-diagonal entries are these first two. And if you know how to take determinants of a matrix like this, you can take a determinant of this block and multiply it by the determinant of this block, right? When you have a matrix that's in blocks, you can take the determinant that way. The determinant of this block is clearly the identity. And the determinant of this 2 by 2 matrix is minus 1. So, and both occur. Because, for example, the determinant of f of e is the determinant of the identity matrix, which is 1, but the determinant we've just seen of f of tau is equal to minus 1. So permutation matrices have both determinants, plus 1 and minus 1, which gives us another homomorphism. Namely, if we take this homomorphism and we compose it with this homomorphism, and we're allowed to do that, right? The composition of two homomorphisms is a third. We get a very interesting homomorphism, which looks like this. Let's call this thing 2, and this one 1. The composition of 1 and 2 looks like this. First, you take the symmetric group by F into the general linear group, and then you compose this with the determinant homomorphism to R star. Now what's the image in the kernel? The image is not all of R star, because the image of F was not all the matrices here. It was just the permutation matrices. And we saw that the determinant of a permutation matrix is plus or minus 1. So the image is the subgroup plus or minus 1 inside of R star. And the kernel, now we have a kernel. See, the original map here had no kernel at all. But now we have a kernel which consists of the sigma such that the determinant of f of sigma is equal to plus 1. Those are sometimes called the even permutations. They're not everything, because tau is not an even permutation. This little transposition is not even. But that's a normal subgroup. Of Sn, non-trivial normal subgroup, and it's called the alternating group on n letters. We're going to see pretty soon that its order is half the order of Sn. So its order is going to be n factorial divided by 2, at least when n is bigger than or equal to 2. The order of An. We're going to prove that pretty soon. Yeah.
I was just wondering, did the notion of the sign of a permutation arise from this, or this is like the...
So, yeah, this is very good. This, because there's a potentially circular argument here. If we've already used the sign of a permutation to define the determinant, this is a little illegal. So no. You have to define the determinant independent of the formula for it. Namely, you have to define the determinant as the unique map, which takes this to this, and multilinear, etc. All right, then... No, it's a good point. It's a good point. Then you have to prove to yourself that the determinant of a permutation matrix is plus or minus 1. And then you have the notion of the sign of a permutation. That's the right way to define a sign of a permutation. The other ways of doing it, you can find in algebra books the definition of a sign of a permutation. The sign of the permutation, by the way, is the sign of this determinant. This is called the sign of the permutation sigma. So for example, this transposition has sign minus 1 and the identity element has sign plus 1. Another way of doing the sign of the permutation, which is completely independent of matrices and determinants, is to prove that any permutation can be written as a product of transpositions, and that the number of transpositions is not unique, but whether they're an even or an odd number of them is unique. And that allows you to define the sign. I wanted to do it this way so that you could see that composing two homomorphisms gives us another homomorphism, whereas this had no kernel, now we have a kernel. Whereas this one was surjective and had all of the group as the image, now we have a non-trivial image. But a good point. I mean, one could get caught up in the circularity of this. I assure you can do it without. Okay, let's just work out in the symmetric group on 3 letters, what's the kernel and what's not. In S3, the identity element sigma and sigma prime, these are the cycles that go around in 3. 1, 1, 2, 2, 3, 3. This is sigma. And sigma prime, which is its square, are even permutations. So are in the subgroup that I called A3, and tau tau prime, and tau double prime are odd permutations. And you can check that by writing down the permutation matrices and taking their determinants. So here, this group had order 6. We see that the alternating group has order 3. Okay? We'll do a lot more on the symmetric group and the alternating group, etc. Now, let me just tell you about another important homomorphism. But first, let me define a notion of a rather natural normal subgroup of a group. Here's the definition. So if you have any group G, the group that's denoted Z of G, which is called the center of G, consists of the elements Z in G that commute with everything. We commute with everything in G. So the center can go all the way from G to the identity. This is a subgroup. In fact, a normal subgroup. As you can check by multiplication and by conjugation. I won't do that for you. These kind of things you should start checking yourself. It's a normal subgroup of the group. We're going to exhibit it pretty soon as the kernel of a homomorphism, which will validate your hope that every normal subgroup is a kernel. All right? The center can go all the way from E to G. For example, if G is abelian, what's the center? If G is abelian, the center is everything. The abelian means the group elements always commute. So G is equal to ZG if and only if G is abelian. If G is equal to the symmetric group on n letters, we're going to see that Z of G is the identity element. There is no element that commutes with all permutations except for the identity. That's not obvious. It's a good exercise to show that no matter what permutation you write down, you can find something that doesn't commute with it. We'll learn how to do that when we get into permutations, have a better notation, etc. If G is the general linear group, and I think Peter ended with this, the center of G consists of the diagonal matrices. That's a famous lambda is in R star. That's a famous result in linear algebra, that if you have a non-diagonal matrix, and by diagonal I mean the same entry on the diagonal. If you have a non-diagonal matrix, you can find something that doesn't commute with it. So this is a very useful notion. To any group is assigned a canonical normal subgroup, quite frequently trivial, which is its center. The center is an abelian group, because if it commutes with everything in G, it commutes with itself. So it's a normal subgroup, which is abelian. There are plenty of groups, like the symmetric group, which have no abelian normal subgroups. So there are going to be many cases where we get a trivial center. Now I said that I would tell you a natural homomorphism of which the center was the kernel. So here's a natural homomorphism. And this is our fourth example of a homomorphism. Rather critical. There is always a natural homomorphism from G to the new group, which are the automorphism group of G. Now let's remember what this is. This is all isomorphisms. Let's call the isomorphism H from G to G under composition. Namely, the group law is composition of isomorphisms. So associated to an element in G, you have to give an isomorphism from G to itself. Let's think about that for a minute. So this is an absolutely critical map. For any group, you have this homomorphism. Let's give us a chance to think. So I have to assign f of G should be some isomorphism from G to G. Any suggestions?
some element of G prime, G by G prime, G times G.
That's a good idea. But that is not a group isomorphism. So the suggestion is, and that's the first suggestion, and it's a good one. We could try the thing that takes f of g, so he's suggesting the following. F of g of an element h in G should be gh, left multiplication by G. That is certainly an isomorphism of sets, right? Because it's one-to-one and it's bijective. If two elements, gh is equal to gh prime, h is equal to h prime, that kind of stuff. But the problem is, we have to check if f of gg prime is that equal to f of g times f of g prime, composed with f of g prime. Well, let's see what this does. This takes an element h to g prime times h. Right? That's the definition under this. This takes an element h. So what does this take an element h to? First it says you multiply by this isn't what I want. Is this honestly an isomorphism of groups? Yeah, of course I want that. Yeah, I know what I want to have, but I mean, is this actually an isomorphism of groups?
Not necessarily. You have to take both of H, so you're going to get G, H, G prime H, and have G prime.
All right, so let's see. F of g prime of h is g prime times h. Correct? Then this I have to apply to this element. Isn't that just multiplied on the left by g?
F of g is not, the way you define f of g is not an automorphism of g.
Why? That's what I want to know. Why is this not a group?
If it's not a
Thank you. Namely, this is not the problem. Thank you. Excuse me. So there's a problem here. I apologize for being so confused. Problem. This map that takes h to gh is not an isomorphism of groups. It's an isomorphism of sets. Namely, if I apply this, f of g, I did it the wrong way, to hh prime, there we go, that has to be f of g of h times f of g of h prime. Got it, right? Thank you. And this is, by definition, g times hh prime. Whereas f of g of h times composed with f of g of h prime is, on the other hand, gh times gh prime. And there's no reason that that's equal to that. So it is not an isomorphism of G as a group. It's a nice set theoretic map that takes G to G, but it doesn't commute with the multiplication in G. So we're going to modify it. I'm going to do this or else I'll dig myself a grave here. We're going to modify it. Modification. Try f of g of h is multiply by g, but then multiply on the right by g inverse. Conjugation by g. Now, again, this isn't the first thing that would have suggested itself to you. What you suggested was the first thing. Why not just try left multiplication by g? But the problem is that doesn't give an isomorphism of the group. I claim this gives an isomorphism of the group. So let's check. First of all, this is in aught g. That was the problem with the first one. It's an actual automorphism of g, because if I apply it to hh prime, I get g times hh prime g inverse, which I can rewrite as g inverse times g h prime g inverse, because these two g and g prime inverse cancel, and then this becomes f of g of h times f of g of h prime. So at least this thing wasn't an automorphism of G. this thing is at least an automorphism of G. Now I have to check, and that's the second thing you have to check, that it's a homomorphism of groups. So at least I have a method of assigning to each element in the group an automorphism. Yeah?
I'm sorry, you're concluding that it's an automorphism by checking that it's a homomorphism. You don't need to show bijectivity also?
Ah, good point. So it's at least, sorry, this shows it's a homomorphism. To show it's an automorphism, we have to show it's one-to-one and onto. Okay, so first of all, we have to show that every element in the group can be written in this way. And then we have to show that if GH G inverse is equal to GH prime G inverse, that H is equal to H prime. You willing to believe me on those two, or do you want me to do it? But you're right, those have to be checked.
Alternatively, you can exhibit an inverse.
We could exhibit an inverse. Very good. Namely, if we're able to show that there's a way to get back to H from this element, and what would be the inverse of this? Conjugation by, right, by G inverse. Very good. That would be even a better way to do it. Thanks. Good, good, good. It's a homomorphism with inverse. And the inverse is conjugation by G prime by G inverse. And now let's check that F is a homomorphism. And there we have to check that F of G, G prime is equal to F of G prime, where this is multiplication in G and this is composition of automorphisms. Well, this is by definition, F of GG prime on an element H is conjugation by GG prime. So it looks like this. Which if I wrote it all brutally out would look like G, G prime, H, G prime inverse, G inverse. You should get used to the fact that when you invert a product, you get the product of the inverses in the opposite order. Because this element has the property that when you multiply it by this, you get the identity. Okay? On the other hand, how about if we take F of G prime of H? First thing is conjugate by G prime. So that would be F of G on the element G prime H G prime inverse. And this automorphism is conjugate by G. So I get G of G prime H G prime inverse G inverse. And if you look at what this does to H and what this does to H, they do the same thing for every H. Therefore, they are the same automorphism. So this is equality in the automorphism group of G. And that's why this map is a homomorphism. So this is really quite cute. And remember this definition. What is the kernel of F? What is the kernel of F? Let's go somewhere where we have room. Here. Well, it's the elements of G such that when you conjugate by them, you get the trivial automorphism. What does it mean that this element is equal to H for all H? That's what I would have if I had the trivial automorphism. Namely, it would take every element in the group to itself. So I'm looking for the elements in G such that this is equal to H for all H. That would be the quantity of being in the that would be the character of being in the kernel of this map. Yeah. Back there?
The center of G.
Exactly. It's exactly the center of G. Because if GHG inverse is equal to H for all H, that says that G commutes with H for all H, which is exactly what we called the center of G. So you remember we said the center was a normal subgroup? I've just exhibited it as the kernel of a homomorphism. what's the image? Do I get every automorphism by this kind of conjugation business? Well, let's take a look at a simple type of group and see whether we get all the automorphisms. Let's take a nice group like the Klein 4 group, which Peter exhibited to you as the set of matrices in 2 by 2 matrices that have plus or minus 1s on the diagonal. Now, that group has 4 elements in it. There's the identity element. There's a matrix of order 2. Then there are 3 different things of order 2. So this could be the matrix minus 1, 1. And this could be the matrix 1, minus 1. And this could be the matrix minus 1, minus 1. And they have the property that if you take the product of any 2, you get the third. So you have to check that, but that's not so hard. So, for example, tau tau prime is tau double prime, etc. Okay. What is the image of F in aught G in this case? Well, what do I get when I conjugate by an element in this group? What kind of automorphism do I get in this group if I conjugate by one of these matrices? Well, is this group abelian?
It is. So we get a...
It's an abelian group, right? The products don't make any difference what order you take them. They're diagonal matrices. So this is abelian of order 4. In particular, G is equal to its own center. Conjugation by anything is a trivial automorphism. So the image of F in the automorphism group is just the identity element, the identity automorphism. So for this group, we get very little of interest in the automorphism group by conjugation by elements in G. On the other hand, I claim that this group has a non-trivial automorphism group. In fact, and this is a nice exercise, the automorphism group of G is isomorphic to the symmetric group on 3 letters. Well, how could that possibly be? I mean, how could I associate to an automorphism a permutation of 3 objects? Do I have 3 natural objects in this group? No? Yes?
It looks like the 3 natural objects would just be tau, tau prime, and tau double.
The non-identity elements in this group must be permuted by an automorphism. Am I right? Because you can't take them to the identity in an automorphism. So if I have some map from G to G, an automorphism, then I can associate to G maybe I'll call these things tau 1, tau 2, and tau 3. So tau 1 times tau 2 is tau 3, etc. Can associate to this A, maybe I'll call A an automorphism so we don't get confused, to A permutation of the set tau 1, tau 2, tau 3, which gives me an element in the symmetric group on 3 letters. Very good. And if I know that element in the symmetric group on 3 letters, I certainly know the automorphism of the group, because I know where it sends tau 1, tau 2, tau 3, and I certainly know where it sends the identity. So that gives me a homomorphism from the automorphism group of G to the symmetric group on 3 letters. And that association gives a homomorphism group with trivial kernel. Because if I go to the trivial permutation, then that means that the automorphism takes tau 1 to tau 1, tau 2 to tau 2, and tau 3 to tau 3. Okay? And my assertion is that this has full image. The image is a symmetric group on 3 letters. No matter what permutation you write down of tau 1, tau 2, tau 3, that is an automorphism of the group. That's not obvious. That's not obvious that if I switch tau 1 and tau 2 and keep tau 3 the same, that gives me an automorphism. But in fact it is. I want you to check that. That's a little laborious. So this is trivial kernel and full image. So here we have a group, the Klein 4 group, where the image in aught G is trivial, but the automorphism group is large. So that this map need not be either an injection or a surjection, and the image are called the inner automorphisms. Image of F are called the inner automorphism group of G. It gets its own name. Those are all the automorphisms that have the form A of H is equal to GH inverse for some G and G. It's an interesting subgroup of the automorphism group of G. And for the Klein 4 group, the inner automorphism group is trivial, and the full automorphism group is the symmetric group on 3 letters. Well, I hope this lecture just gives you an idea of how flexible this notion of homomorphism is. It's a way of seeing which groups are related to others. This already is pretty sophisticated here, that we start with the Klein 4 group and that there's a map between its automorphism group and the symmetric group on 3 letters. Another way to see this, by the way, for those of you who like, how many of you seen finite fields? Forget it. We'll do it later. We'll do it later. Not to preview anything that'll just confuse people. There's enough that's confusing already. So try to get with this language. We're going to have homework on the web. We're going to have section this week. Thank you. No drinking in class. Sounded like an open container to me. I have to worry about these things now as dean. Who is doing the section on Tuesday? Liz. And Jace is doing the section for the extension school people, none of whom should be in this room. When? Tuesday also? Tuesday at 7:30. That's posted on the e-web page, and you guys shouldn't go to that because Jace has enough to do with the extension school people. So Liz will be holding forth this Tuesday. If you have any questions about the web page, etc., please speak to Peter about it. By this point, I hope everyone's signed up for the course and ready to go. Okay, see you Wednesday.